All right, good morning, everybody. So at the last lecture, I introduced the concept of a pointer to you. Now, a common complaint in many of the fourth year courses that use C or C++ is that when the students go to do the assignments, they get some code, the code involves a bunch of pointers, and they can't actually do the assignment because they don't know what they don't have a good understanding of what a pointer is or how to use one. So I'm going to take a little bit of time today to review exactly what a pointer is and why you might want to use them. So remember what a pointer is. So a pointer in C holds the address of a hopefully already existing object. Right, so that last part's quite important. So when you make a pointer, you want to make sure that you have an object already that the pointer can point at. Right? You want to avoid using a pointer whose value is uninitialized because you don't know what that thing is, what the pointer is pointing at. And when you create a pointer, you always want to set the pointer so that it points at an object that is existing and will continue to exist in the future. That last part is also important in a language like C or C++. All right, so remember, if you have a type T and you'd like to make a pointer to an object of that type, you write T star. And so swap here has two parameters, X and Y. Right? Both parameters are pointers, right? They are double star. So that means X is a pointer to a double value and Y is a pointer to a double value. The swap function here swaps the values pointed at by X and Y. Right? So this is important. It doesn't swap the pointers X and Y. Right? It swaps the values that the pointers point at. So if X points at an object owned by the caller and Y points at an object owned by the caller, then swap effectively swaps the two objects that are owned by the caller. Right? So how do you actually swap the objects pointed at by the caller? Well, you need some way to get the object that the pointer points at. Right? And so that operation is called a pointer dereference. So given a pointer X, if you write star X, that gives you the object that X points at. So in this case, star X gives you back a double value that the caller of the function owns, right? Or has, the caller of the function owns, right? Star X equals star Y, what does that mean? Well, star X gives you the object that is pointed at by X, right? And star Y gives you back the object that is pointed at by Y, sorry, right? And so that takes the value of the object pointed at by Y and stores it in the object that is pointed at by X. Right? And then star Y equals temp takes the value temp and then stores that in the object that is pointed at by Y. So when the caller calls the function swap with two values A and B, or more precisely, they call the function passing in the address of A and the address of B, right? The swap function manages to swap the values 1.5 and 99.9 with A and B. Right? So in other words, A becomes 99.9 and B becomes 1.5. Right? And so in a language like C, this is how you would write the swap function. In a language like Java, you can't do it because Java doesn't have pointers. Right? And so you can't swap two primitive values in Java by calling a method. Right? There's no way to get the address of a primitive value or get a reference to a primitive value in Java. Right? Okay, so we have a pointer. Right? We have pointer dereference. We have the address of operator. Right? So and A and and B, address of A, address of B. Right? The address of something is a value that can be stored in a pointer. All right, so there's an example of when you might want to use a pointer. Right? You want a function to be able to modify or change values owned by the caller. Right? Another example is when you would want a function. So actually this is the same application, but it now solves a slightly different problem. Right? You have a function where you want to return more than one value, or I guess more precisely, the function wants to compute several things and you want to communicate all of these things back to the caller. So here max finds the maximum element or the maximum value in an array A, and it also computes what is the index of the maximum element in that array A. Right? So if you want to communicate both pieces of information back to the caller, you can't in C because a C function can only return one value. So here we're going to return the maximum value. And to communicate the index of the maximum value, we're going to ask the caller to give us a pointer to an object where we can store the index. And so that is that pointer right there. Right? And so index is a pointer to a size t object where the function max can write the value of the index into. Remember in C doesn't know how big an array is. So if you want to iterate over the elements of an array, in this case we want to iterate over A, your function probably needs some way to know how big is A. So typically what happens is there's a second parameter that is the size of the array, right? So here count is how many elements are in the array A. And so this is just the usual max function, right? Iterate over the elements of the array, you look for the biggest element. The only interesting part in this code is that line right there, right? We want to write the index of the maximum element into a value owned by the caller. So we dereference the pointer that the caller gives us, right? That gives us a size t object that we can write the index into, right? And you do that just by using simple old assignment. And that lets the max function communicate two pieces of information back to the caller. Right, now when you call the function, the caller has to remember they need to pass a pointer in for that last argument right there. Right, so they need to pass in a pointer to a size t object. Also remember, when you're using pointers, you probably want the pointer to point at something, right? So in other words, you need an object to point at. So there is my object that we're going to point at, right? So the function is going to write into the variable I the index of the largest element in my array ARR, right? To pass the pointer to I, you take the address of I, like that, right? So a common mistake, so this is the exact same code except we're going to make a mistake in the main method, main function. So a common mistake made by new programmers to C is that they say, well, I need to pass in a pointer, so I'll make a pointer. They'll write something, they'll write something like this. Right, so they'll make a pointer to a size t object. Right, the pointer is uninitialized and there is no size t object that the pointer is pointing at. And so when the function, and so they can now pass in I directly because that is a pointer. So now when the function tries to write into the object pointed at by I, there is no object, and so you end up with an error. So when you run that program there, it crashes down here, right? Executable exited with a code of -11, which it basically is the way that C is telling us that there is a problem when you ran your program. All right, so there's another example of why you might want to use a pointer, right? You want to, you have a function that would like to communicate information back to the caller, right? One way to do that is through a return value. Another way to do that is for the function to write into an object owned by the caller. And finally, yet another reason why you might want to use a pointer is because your program might involve objects that occupy lots of memory, right? And so this max function here, there's a few, it looks relatively simple. Once you get used to pointers, it's a simple function. But there is something here that might be a little bit confusing, right? So this function here takes in an array A. Right? And you know that in programming languages, arrays have no fixed, or there's no well, that's not true. There's, the arrays can be very large, right? So in C, you can make an array that has up to whatever the maximum value of size t is elements, right? That maximum value is quite large. So on my computer, it's probably on the order of 2 billion, I'm guessing. Could be bigger. It's probably bigger, actually. It's probably closer to 4. It's very large, right? So that array there potentially occupies lots of memory, right? I don't know if I ever told you this in 124 or if you know this already. So when you create an array in languages like C and Java, the language is the basic guarantee that the elements of the array are stored together. Right? So the first element is stored beside the second element, which is stored beside the third element, which is stored beside the fourth element, and so on and so on and so on and so on. So you have a very large array that occupies a very big chunk of memory. Now remember in the previous lecture I told you that C passes arguments by value. So if you have a function in C, if C passes arrays by value, what does that mean? It means it copies the entire array into the function. The array is very big, that takes a lot of time, and it also may not work because the space where functions live in a C program is different than where they live in a different area of memory than where your things like arrays typically live. And the space that functions have is much smaller than the space where other stuff can live in. So if C actually passed arrays by value, there's a good chance that there would be the maximum size of an array that you could pass is smaller than you'd want it to be. And it's not just arrays that have this problem. Remember, there are these things called structures in C. Right? Structures can also be very large. Right? If you have a structure that has many members, right? All of those members require memory. Right? C does pass structures by value, so that means C copies all of the members for a structure when you pass a structure to a function. If the structure is very large, this takes up a lot of memory and it takes up a lot of time. Right? Okay, so it turns out that C does not pass arrays by value, it does something else. Right? But this issue of large objects we can show, where's my code? I'm going to show you with the little program here. Okay, so here's a little C program that makes a structure called big. Right? Big has one member called length, and then it has an array inside of it of size, in this case it's of size 1024. Right? But you can imagine that this could be a much larger number here. Right. Now, what the language says about structures is the members of a structure are stored beside each other in memory. So here you have a field of type size t. Here you have an array of length 1024, and so that means that the structure in memory takes up at least that much space, however big a size t is, plus at least that many times the size of car, right? So 1024 times 1, because the language says that cars occupy 1 unit of memory. Right? And so this thing here occupies a not insignificant amount of memory. Right? If this number was bigger, obviously it would take up more memory. Right? Okay, so when you run this program here, it computes the size of one of these big structures and then prints the result. So if we run that little program, like that, right, it tells you it's 1032 units big. Right? That turns out to be the 1024 plus the size of size t. Okay, so why does this matter? Right? This matters because C passes structures by value. So if you write a function that takes in a struct big object, like that, right? This is going to do nothing, so I'm just going to have a blank comment here. Right? So when you call f passing in, I need to make an object. So struct big some object, like that, right? When you call the function f passing in some object, right? What C does is it literally copies, some obj. So what C does is it literally copies all of the bits for the length and all of the bits for that array and passes that as a new struct big object into this function here. Right? And so passing around large objects is memory intensive and time intensive. And so you want to avoid doing this sort of thing. Right? And so if you make this structure big enough, you won't actually be able to call this function. You'll run out of stack space. And so the solution here is to not pass in a structure by value. Right? So the solution here, if that thing is very big, is to pass in the structure by pointer. So here I'm going to change that to p obj. So pointer to object, right? And there you would pass in the address of the object. Right? Why does this work? Because pointers are relatively small. Right? So the size, remember what a pointer stores? It simply stores a memory address, which is just a number. And so the size of a pointer on my computer is 8 units. And so that's not a large amount of memory. And so using pointers to transfer values transfer arguments to a function and to return things from a function requires much less memory to call and return the value. Right? And so the large object problem is another reason why pointers exist. All right, so what you got a pointer, you know that you can you can use the pointer to store the address of an object. You know that you can get the address of an object using the ampersand, right? What else can you do with pointers? So it turns out you are allowed to compare pointers. Right? So you can compare if two pointers are equal using equals equals, right? And you can compare if two pointers are not equals using not equals, right? Now remember what a pointer is, right? A pointer is a memory address. Equals equals and not equals, what do? They compare the values stored in P and stored in Q, right? So they compare the values stored in P and stored in Q. So they compare the memory addresses stored in P and stored in Q, right? They don't compare the underlying objects themselves, right? So you can write P equals Q or P not equal to Q, right? Sorry, when you write that, what result do you get? Right, so you get back true if P and Q are both null pointers, right? So if P and Q both their values are both null and the pointer types are of the same type, you get back true, right? Okay, so if P and Q are equal and they're not null, then you know that both P and Q are pointing at some object, right? And in fact, they're pointing at the same object, right? So both pointers point at the same object. Then P equals Q should be true, right? This is the same thing in Java when you write x equals y, and x and y are two references, right? What does it mean? It means the references are equal, which means they're both pointing at the same object. Okay, so later on we'll talk about arrays and how pointers interact with arrays. So if you have a pointer that is a pointer to an array, and your second pointer is a pointer to the first element of the same array, then it turns out P equals Q is also true. Right. If you have a pointer to a structure and the second pointer is a pointer to the first member of the structure, it turns out that's also true. Right. And finally, there's something called the too-far pointer, which we'll look at in the arrays notebook. So if you have the too-far pointer for the same array, you have two pointers that are equal to the too-far pointer for the same array, it turns out the pointers are also equal. Right? For the time being, these are the only two interesting ones for us. Right? In a few lectures, when we talk about arrays, we'll have to discuss the other three cases. Okay, so the first two cases, let's take a look at them. X and Y, they have the same value, right? They're both 1. So if you write x equals y, the answer is true. Right? Now, if I take a pointer P and Q, and I make P point at x, and I make P point at y, right? And I now compare P and Q, right? That doesn't mean, so remember what that means, right? If P equals Q is true, that means they are both pointing at the same object, right? Here, P points at x, Q points at y, right? This should not print out P equals Q, right? It should print out P not equals Q. And in fact, it does, right? So P is not equal to Q, which is good, right? If P and Q are both pointers of the same type and the values of both pointers are null, then they should be equal. And so this should print out, P equals Q. Right? So the interesting one is this one is the first case here, right? Remember, so P and Q, they both point at different objects, so they are not equal, despite the fact that the values being pointed at are in fact equal. Right? If you want to test are the values being pointed at equal, you write star P and star Q. Right? So dereference the pointers. Right? That gives you the underlying objects. So this one in this case gives us x and it gives us y. So is 1 equal to 1? The answer is yes. I guess I should change these. Star P equals star Q. I should change the other one too, but I'm not going to. Right? Boop, boop, boop. And now star P is equal to star Q, right? The value being pointed at is equal to the value being pointed at by Q. Okay, what else can you do with pointers? Well, if you can compare them for equality, you might guess that you can compare them for magnitude, right? So less than or equal to, greater than or equal to. So it turns out you can, but again, we're gonna save that discussion for the arrays notebook, right? And finally, you can also do arithmetic with pointers. And this is where things get really somewhat more complicated. So if you have a pointer, you can add and subtract a value to it. So you can add and subtract a value and or subtract a value from the pointer to get a new pointer. And so that turns out to be very useful. And again, we'll talk about that when we get to the arrays notebook. All right. Okay, so there's your introduction to pointers in C. Right? You're going to be seeing a lot more of them as we progress through the course. Any questions about pointers so far? Yes?
To scroll back up to the maximum value?
Sure can.
So in a recursion stack,
Yeah.
does C also keep copy and paste the values, or does it not?
What do you mean by copy and paste the values?
Like when we have an object
Yeah.
and we pass it through a function,
Yeah.
It doesn't necessarily count the object itself, it counts the value. So if you have a recursion in that
Yes.
case, I'm asking.
Yeah, so in a language like C, every time you run, so if you recursively call a function, right, every function invocation gets its own space, right? So in other words, you get basically a new instance of the function, right? So however C is transferring values to the function, that gets repeated when in the recursive call. So if you have a function f, it has an int, right? You call the function f, so that copies the value of the value of the argument into f. If f calls itself, the new version of f gets a copy of the argument that was passed to it, and so on and so on and so on. That's why you eventually run out of space. So if you have a recursive function that runs for that's very deep, right? Eventually you run out of what's called call stack space. Yeah. So that's what's happening. Any other questions? All right. In the next notebook, structures. So we've already seen structures a little bit in the course, so I introduced them when we talked about types. We're now going to look at them in a little bit more detail. In particular, what happens when you have a pointer to a structure. Okay, so just to remind you what a structure is. So we saw an example of one back here. So a structure is C's way of creating what's called a compound type. Right, so in other words, it's C's way of letting you aggregate one or more pieces of data into a single place. Right, so here our struct big lets us aggregate two pieces of information, right? A value called length and an array called data, right? And it lets us aggregate that into one thing called struct big. So that's sort of what a class does in C and Python, right? A class lets you aggregate data into a single place in Java. So in Java, though, a class also lets you aggregate the methods that operate on the data into that same place. So C doesn't have that second part, right? So there's no way that you can put functions into a structure. I was going to say something, but I'm going to ignore that. So you can't put functions into a structure. Right, but you can put data into a structure. So a structure is kind of like a poor man's class, right? It lets you aggregate a bunch of data into one place. Everything is public in the structure, right? So C doesn't have access modifiers. So if someone can see the definition of the structure, they have access to all of the members of the structure directly by name. Every time you make a structure, you get a new type, right? The name of the type is struct followed by the name of the structure. The members of a structure, I guess this is important. The members of a structure can have any type, with one exception, right? You're not allowed to have what's called a variable length array in a structure. So in other words, you're not allowed to have a structure where the array size can change, right? Or the array size is defined by another variable. There is an exception to that rule, but we'll ignore that for now. You can have an array of constant length. So here, right? That 1024 is a constant, that's fine, right? But that can't be a variable name, except under the one exception, right? Okay, so to declare a structure, if you want to declare a structure but not define it, you use what's called a struct declaration, right? Or a forward declaration of the structure. So when you write struct and then you give it a name and then a semicolon, right? That simply says there is a structure having the name tag name that exists somewhere. Right? It doesn't say what the definition is, right? But it lets the compiler understand that there is a structure whose name is tag name somewhere. If you're wondering why this is called tag name, it's because this is what the language says the names for structures are. They are things called tags. You are not allowed to have two tags with the same name in the same program. However, you can have a tag that is the same name as a function or a variable, which is confusing, but that is allowed. Okay, so if you want to define the structure, then you write struct tag name and then some braces, and you put in the members of your structure, right? Just like I did back here, right? And so there are the two members of our structure in that example here. There's our point2 structure from earlier in the course, right? So a point2 is just a structure that represents a two-dimensional point having real coordinates, right? There are our two members x and y. Once you make a structure, you can make a variable of that type, right? So the type name of the structure is struct and point2, right? So struct is part of the name. Struct is part of the type name. So to make a variable of that type, well, you just write the type name and then you give it a name, so p. So p is a struct point2 object, right? Unlike, so you don't need the new operator here you don't have to write anything special to create an object of a structure type, right? In Java, you have to write new and then blah, 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 blah to get a new object, right? That line there actually makes a point2 object p, right? So in other words, there is some memory that's allocated. That memory can hold two double values called x and y, right? And that thing gets allocated for you and it lives somewhere in memory. Right? This has automatic storage. So in other words, if this is inside of a function, after the function returns, p disappears, right? To access the memory, wait, what's going on? Okay. We haven't talked about malloc yet, so this line here is going to be a little bit confusing here. You can make a pointer to a structure. So here is a pointer to a structure, right? Now, if you want to dynamically allocate memory for the structure, you use this function called malloc. Well, sorry, if you want to dynamically allocate memory for anything, there's a function called malloc that will let you do this, right? And so this particular piece of code here makes a pointer to a structure. The next line, the call to malloc allocates memory for a struct point2 object, and it makes p point at that object that was just allocated there. Right? We'll talk more about this when we get to the arrays notebook. Right, another way to make a pointer to an object would be on the next line here. You could write struct point2 star ptr equals the address of p. Right, so pointers to structures are exactly like this, are exactly like pointers to anything else in the language. Okay, to initialize a structure, so back here, this is an uninitialized structure. Right, px and py could have any value. If you want to set the values when you create the object, you just use the braces. Right, so struct point2p equals brace 0.1 and 0.2 sets x to 0.1 and sets y to 0.2. There are a bunch of rules related to how initializing the structure. I don't care if you know them. Right? If you work with structures a lot, eventually you're going to want to know exactly what they are. Right? For the most part, though, I mean, in this course, every time you make a structure, just assume that you're going to initialize all the members, right? Or you're going to set the members later on yourself. Right? If you want to know what the exact rules are, they're listed here in the notebook. Right? This is what I expect you to know in this course here. If you want to, you can also initialize the members by name. So you can write x equals 0.1 and y equals 0.2. The order doesn't matter, right? You can write y equals 0.2 and x equals 0.1. Right? Again, I don't care if you know how to do this in this course. Right? Okay, to access the members, you just use the dot, right? So it's exactly the same as Java. I guess more precisely, Java is the exact same as C, right? This is where Java got its dot notation from. So here's my structure. Again, it's got two fields, two members x and y. Here's my point, right? Its x value is 0.1, its y value is 0.2, right? If I want to get its x value, I just write p.x, right? Similarly, if I want to get its y value, I just write p.y, right? This is exactly what you would write in Java with a class that has public fields. If you want to change px and py, well, you just write px equals something, and you just write py equals something. I'm not going to run this. It gives you back exactly what you expect to get. Okay, so what I haven't told you yet is, so we actually talked all about this when I introduced structures earlier in the course. What I haven't told you about, though, is what happens if you have a pointer to a structure. So if you have a pointer to a structure, why did I use malloc here? I shouldn't have done this, sorry. Let me change this, because the notebooks are written sort of out of order. So let me make a structure up here first. So struct point 2. So I'm just going to make the object here 0.1, 0.2, because I guess those are the values that we're using. Okay, so I can make a pointer to a structure object, right? How do you do it? Well, you just take the address of the object. So obj, right? Okay, so if you want to get access to the, so here's P points at a structure, right? If I want to get access to the X member of the object that P points at, what do? Well, one way to do it is you dereference P, right? That gives you obj, right? Then you can write .x, that gives you the X coordinate of obj. So you need the round brackets here, unfortunately, if you're going to do it this way, because it turns out dot has higher precedence than the pointer dereference. So if you don't write the round brackets, it tries to do p.x, which doesn't work because p is a pointer, right? So you need the round brackets if you're going to do it this way, which is why most C programmers don't do it this way. Okay, so star p gives you back the object that p points at. That gives me obj, right? Which gives me obj.x equals 100 and obj.y equals 200. So this, not surprisingly, when I print, why did I do it this way? Oh, yes, right. So when I print out those values, there's something missing here, right? No, that's fine. When I print out those two values, we're going to get 100 and 200. Right there. Okay, so so if you have a pointer to a structure, it's a bit awkward to write the round brackets and the star. And so instead, C gives you a shortcut way to access the members of a structure where you have a pointer to the object, right? And so the short form is to use the arrow operator, right? So pointer, arrow, so that's the hyphen and then the greater than symbol, right? Lets you automatically dereferences the pointer for you, right? If it's a pointer to a structure, right? This only works for structures, right? So p arrow, if p is a pointer to a structure, dereferences the pointer p for you and then accesses the X member, right? The next line, p arrow, dereferences p for us and then accesses the member y. So most C programmers, when they're working with pointers to structures, will use the arrow operator rather than parentheses star, right? And so when you run that code, you see that the coordinates of p now the coordinates of obj now change to -1.5 and -2.5. Right? So the arrow operator with structures dereferences the pointer and then gives you access to the member. All right, so structures sort of look like Java classes. It turns out they're not, right? Because in Java, when you have a object, you always have a reference to an object. So assignment in Java means you are assigning to the reference, right? That's not how they work. That's not how it works in C. So in C, when you assign to a structure, you actually overwrite the values in the structure. So here's an example here. P is a structure, right? It has X and Y values 1 and 2. On this line here, Q is a structure. You don't know what its X and Y coordinates are, right? You are allowed to assign P to Q, right? So what that means is, so P and Q are two distinct objects here, right? This is the confusion that happens if you come from a language like Java, right? So in Java, if you wrote Q equals P, that means Q and P both point at the same object. That's not what it means in C, right? Here, it means P and Q are separate objects, but Q, all of its members are copies of the values of the members of P. So literally what happens is the memory of P gets copied into the memory of Q. Right? So the value 1.0 gets copied into QX, the value 2.0 gets copied into QY. Right? So in C, you would in Java, you need a copy constructor to do this. In C, you just use plain assignment. Right? So there's P, there's Q, there's our assignment, right? R equals Q means exactly what you hopefully think it means, given what I just told you, right, it means copy the elements of Q into the, copy the members of Q into the new object R. Right, so when you run this piece of code and print out px, py, qx, qy, and rx, ry, not surprisingly, they all print out the same thing. Right, they're all the same thing. Do I actually change them? I should try to change. Let me try to change them after here. Right, just to show you that they are in fact independent structures. So r dot x equals -1 and r dot y equals -2. Right, and then I'm going to copy these lines of code here again and print out their values again. Right, so P, Q, and R, they all have the same coordinates. Right, after I change R, right, P and Q don't change, but R does in fact change. Right, so these are in fact three separate structure objects here. Right, they all have their own independent x and y coordinates. The same is true if one of your members is an array, right? So the elements of the underlying array all get copied into the other structure's array. Okay. So here's a structure that contains two strings, right? Assigning one structure object copies the contents of the arrays, so the two structures end up having independent copies of their strings. So here's a course info structure, right? So this would be like a Queen's course. So there's your code, so CISC 220. Here's your title, systems programming, right? These are supposed to be proper strings. Remember, they should have a, after the CISC 220, there should be a \0. After systems programming, there should be a \0 in the array, right, to indicate the end of the string. Okay, so how do I make a course info object? Well, I can, I write struct course info, give it a variable named C. Right, now I'm going to initialize the code and the title. So it turns out this works for strings. Right, I can initialize that array by writing in a string, and I can in fact initialize that array by writing in the string. Right. Once you've created the course structure, once you've created C though, remember you can't assign to code and title anymore. Right, code and title are arrays. You can't write C dot code equals something. Right, there is no assignment to an array variable type in C. Right, but you can initialize them, so this is fine. So there's C, here's I. Right, so I equals C means make a copy of C stored in I. So literally what happens is that array gets copied into I, and that array gets copied into I. Right? And I can now change the code belonging to my object I. Right? Remember, I can't assign to code, so I can't write I code equals something. Right? But I can go into the array and now fiddle with the elements of the array. So what am I doing here? I7, set it to B. Okay, sure, we'll set that to B. Right? Oh, wait, I'm going to change the A to a B. Right? I'm now going to change the title. All caps. Am I calling it title? Yes. I'm now going to change that, sorry, into all caps systems level programming. Right? I shouldn't have done it this way, but anyway, I did it. This is showing you pointer arithmetic here. I'll explain this in just a second. I claim that this in fact changes all the letters to capitals. Right? And then I'm going to print out the code and the title. Right? So when I print out the code and the title, remember they're strings. So I'm going to use the %s conversion twice, right? Once for the code, second time for the title. Right, so that should print out sys220b and then systems level programming in all caps. And the original C should be unchanged if what I told you is all true. And happily what I told you is all true. Right, notice that the original object C is unchanged still. All right, so let's go back to this while loop. While star letter, fascinating. Okay, so what's going on here? So letter is a pointer, right? And I initialize the pointer by writing in ITitle, which looks weird, right? Because remember what ITitle is? ITitle is that array belonging to the object I, right? So it turns out that if you have an array you can make a pointer that points at the first element in the array by writing just the name of the array, right? So iTitle is the array, right? It's also a pointer to the first element of the array, right? The element in the array is a car, so that means that the first element, a pointer to the first element should be a pointer to car. So letter here is a pointer to the first character in the title belonging to the object I. Right? So in other words, it's a pointer to a capital S. Right? Okay. So what's star letter? So star letter dereferences the pointer. Right? So the first time through the loop, I get a pointer to the S. Right? Second time through the loop, I'm going to get a pointer to the, well, so I haven't explained why, but the second time through the loop, you're going to get a pointer to the Y. Third time through the loop, you're going to get a pointer to the S. Eventually, you're going to get to the G, right? And letter will be a pointer to the G. The loop runs one more time. You're going to get a pointer to whatever is sitting here, right? Now, this is a proper C string. You know what's sitting there, right? It's the null terminator for the string. The null terminator has a value of 0, right? So if that's 0, that means false. So the loop ends, right? So this is a common pattern for iterating over the characters of a C-style string, right? You get a pointer to somewhere in the string. You iterate as long as the pointer is not the null terminator, which is what that while statement is saying. Right? Okay, so how does this turn things into uppercase? Well, I have a pointer to a character in a string, right? So if I dereference the pointer, that gives me the character itself, right? So if I dereference the pointer, I get the character itself, right? Which I can then pass to the toUpper function, which computes the uppercase version of a character. toUpper is defined in string, I think, string.h, right? So that gives me a character, the uppercase version of the character, which I can then store back in the object pointed at by letter, right? So in other words, I can go into the array and replace the character in the array with the uppercase version of the letter. Okay, what does letter plus plus means? Well, letter is a pointer, right? And in this case, it's a pointer to an element in the array. So letter plus plus means advance the pointer to the next character in the array, right? And so we'll see this in more detail in the arrays notebook. So that's what's going on here, right? So that's what that loop is doing there. Okay, any questions about that example there? All right. Okay, so remember exactly what a pointer is, right? Remember, a pointer is a memory address, right? So, exact same example here, except this time the title is not an array, right? This time it's a pointer to something, right? It's a pointer to car, right? So here, I'm going to dynamically allocate the array that stores the title. Again, we haven't talked about dynamic memory allocation yet. We'll get there eventually, right? But this is the exact same information, except the way that I treat the title is different, right? The code is still an array of size 16. The title is going to be something else, right? So here's my code. There's my course, right? So I start out with the code being sys220A. In this particular case, the title is a null pointer. So that's the way it works for structures, right? If I don't initialize the title field, it gets set to the null pointer. So it gets set to the value 0, right? If I want to store something, if I want to treat this as a string, I need an array to point at. So I'm going to make an array to point at by using the malloc function. Malloc32 allocates an array of size 32 cars, right? So I now have an array somewhere in memory, and I can now write into that array if I want to, right? It looks like it's a pointer, right? But I can treat it as though it were an array, right? So I could write c.title square bracket 0 equals s, c.title square brackets 1 equals y, and so on and so on and so forth. I don't want to do that. I want to copy it. There's a string copy function that copies one string into another string, right? So string copy copies that string, copies that string into the memory pointed at by that value there, right? So if ctitle is an array, in this case it's a pointer to the first element of the array, right? It will copy that string into the array. It also copies the null terminator. Okay, so what happens now if I write that? right? So what if I write I equals C, right? Exactly what happens, right? So remember, the memory for that gets copied into I. So the code gets copied into I, right? The memory for this gets copied into I. Right? Now remember, what is title? Right? Title is a pointer. So what you end up copying is a copy of the pointer. Right? You don't get a copy of the thing that the pointer is pointing at. Right? You copy the pointer. Right? So now you've got two course info objects that both point at the same title object. Right? So they're both pointing at their titles both point at the same string. Right? So if I go into I and I make the exact same changes as before, right? Watch what happens to C. Right? So there's the original value of C at the bottom. Right? When I fiddle with I, right, the course code changes to sys220B and the title becomes systems level programming, right? So now look what happens to C, right? The code doesn't change, right? Because remember, both objects have their own independent code object, right? They both have their own independent array, they both have their own independent array, right? But they're both sharing, they both have their own independent pointer, but the values of both pointers are equal, right? So that means they both point at the same string, which in this case is the uppercase version of the string, right? So you have to be very careful about what it means when you copy stuff. This is true in all languages, right? So you have to be very careful about what it means to copy something, right? In this example here, when you copy the structure, you get an independent copy of the array called code, right? You get an independent copy of the pointer called title, but you don't get an independent copy of what title points at. Okay, so that's the lesson there. I guess we'll stop there for today. Any questions about today's discussion? All right. See you on